Good morning, everyone. Mike and I are going to be talking about something we call Microwatt. Before I start, probably the most contentious thing in terms of the whole project has been the name. Microwatt has nothing to do with power consumption. It was an internal code name. It was based on a play on words around a tiny power core, microwatt. And probably the most number of questions and concerns and abuse I get is about the name. I'll start by reiterating a bit about what Mendy said earlier. This came out of the announce we had 2 months ago, and that was basically where we took the instruction set architecture for Power and released it in an open format. And that means it can be implemented royalty-free with a patent grant. Basically, anyone out there can start building chips. So Mike and I are primarily software developers. We work a lot with the hardware team, but we thought a couple of months before this announce, we need something cool, we need something interesting to show. And so wouldn't it be great to build our own CPU? And as two software people who have never done hardware, we thought, how hard could it be? And so that was about 2 months before the announce. The good news was we did get something out the door. It worked. It was functional. It was maybe not the most compliant, the most competitive CPU out there, but we'll talk a little bit about where we were and where we are today and how it's growing. And as I said, this was just 2 months ago that we announced this. So 2 months ago we came out at the last OpenPOWER Summit and announced it was open. And we threw Microwatt out the door that same week. And so it went up on GitHub. A couple thousand lines of VHDL, pretty simple. And it was really basic, really simple, but it worked. And you could take it, you could build it, you could run it, and it was a 64-bit PowerPC core. What do we have at release? And so with all good demos, there was a bit of smoke and mirrors. It was very simple. We keep stressing it's a tiny power core. It was functional, it wasn't particularly fast. We used what we call the OpenISA fixed point or scalar subset. The idea here was, Power, as all server architectures, has a lot of instructions. And if you get into the vector space, there are hundreds of vector instructions. For the most part, a lot of applications don't need that. In our high-performance computing world, it's bread and butter. In a lot of these applications, BLAS libraries and everything, absolutely need vector. But for your run-of-the-mill applications, you don't need it at all. So, if we were to implement the entire ISA as it stands today, it would have taken us a long time. So what we did at announce, we basically said there was the server subsets, so the Linux and the AIX ones, but there are also two below it. And so we're talking what we call the fixed point or the scalar subset and the scalar subset plus the floating point. What does that mean? Well, there's only like 100, 120 instructions to implement and a lot of variations on a theme. So there's 10 different add instructions, 10 different rotate instructions, 20 or 30 load and store instructions. When it comes down to it, it's a pretty simple architecture in its risk. So there isn't a lot to implement. We used VHDL 2008, so we're trying to use a more recent standard. One thing is, we all complain about the state of compilers in the software world, support for C++, blah. Support in the hardware world is terrible. So VHDL 2008, what's that, 11 years ago? All these tool chains are still coming to terms with it. And now we've got VHDL 2019. We'll probably get that in maybe 10 or 20 years. So we tried as much as possible to use these newer standards because, for example, VHDL 2008 does make life a lot easier in some points. Better for us as a software developer to use high-level constructs, not really program at the low level. And I would say that did help, using a more modern language. But we did have to fit it in with the various tool chains that we used. It was what we call single issue in order, basically one instruction in the pipeline at a time. That means life is so easy. You don't have to think about your hazards, and you don't have to think about pipeline conflicts and all this kind of stuff. And we used we concentrated on one vendor, Xilinx and the Vivado toolset. We had a lot of experience with Xilinx FPGAs, obviously, with our partnership with Xilinx. And internally, we also, I could rely on some people like Liu Yong, who'll be talking later on in the FPGA track about, her work. We have some experts in that field. So when I got stuck, I had someone to talk to. The other important thing we did was very quickly we built a make check, an ability to say, did I break anything? And in the world of hardware, it's very easy to break something subtly and very difficult to find where it went wrong. So one of the best things we had was a make check. Every time we did a commit in GitHub, it runs make check. Did we break anything? Did we subtly break this instruction? All that kind of stuff. And so that's where we were at announce, and that was about 2 months ago.
So since then, we've had a bunch of developments. It's been a fairly active project. And so this is kind of a list of things we've been doing since that release. So we added an I cache and instruction cache. We also have a data cache now as well. And it is a configurable, sets those zip away cache, so you can sort of configure it as you need. We added a bunch more instructions, some that were missing. So the divide instruction that compilers do actually spit out. We didn't have that at release, but we've added that now thanks to some work by Paul McCarris back in our lab. So that's great. We've got absolute branches. These aren't really used very much, but it's nice to sort of finish off that set of things. We've added some pipelining. So Anton said before we are single issue, but we added pipelining up to the decode stage now. So decode's where you start actually pulling in state, and before you start committing any state. So we do have pipelining up to decode, and Anton's going to talk a little bit more about the pipeline later on, so get a few more details about that later on. We moved the design a little bit to adding registers on the output. So each of our individual pipeline stages used to have registers on the input. Registering on the output's more what people are familiar with, so we moved the design over towards that. And as Anton said, we've been concentrating quite a bit on the Xilinx parts, specifically the Arctic 7. Microwatt isn't really designed for any specific FPGA or any specific technologies, but this is what we have at the moment, and this is what a lot of our developers have, these Xilinx parts. So we've been spending a lot of time making sure they do actually work well on these parts. So GPR file, we made sure we got into LUTRAM now. That saved a whole bunch of FPGA resources. And the iCache and the Dcache is now in block RAM, so that saved a bunch of resources. Have another list of stuff that we've done. So we've got a nice JTAG debug interface that Ben Herenschmidt added in his spare time. So you can now actually debug your software running on the FPGA and in simulation as well. Simulation's a bit easier, but you can actually connect this JTAG debug interface into that. It's got a nice little command line tool as well. We hit 100 megahertz timing, which is great, about half of the course for FPGAs. At release, our UART was, we just had some basic and some PowerPC instructions that were illegals that we used to do put char and get char. We now actually have a simulated UART so that we can use that in sim and the same UART in the FPGA. So we're removing the differences between what we have in sim and what we have in FPGA with this. We've had 96 pull requests merged in GitHub. A lot of these are actually Anton kind of merging his own code, but it shows that we're getting it out there into the community, so people can comment on it before it goes in. So everything goes out onto GitHub before it goes into the main tree and gets merged through GitHub. So if you want to contribute, we contribute in the same way that anyone else contributes. We don't just push out stuff that no one gets to see before it's in there. There's a bunch of unit tests for individual pieces inside. So Anton talked about make check. That's for the final built thing. These are unit tests for each of the individual units. There's a bunch of those as well. It's a nice little hello world assembler. So it just prints out hello world and echoes back the characters you type, which is nice to get going. For people just starting, they just want to build something and sort of make sure that it kind of works. You always need hello world, right? We have Travis. So every pull request that goes up there is a Travis, and it gets built. It gets a subset of our make check, so we can have some confidence that pull requests that are coming in are accurate and not going to break anything. And someone turned up and gave us a logo. So Anton showed the logo before. That's cool. So we've got a logo now. How great is that? So all of this work, we made this nice little graph of this is LUT usage over time. So LUTs are the basic primitive you get inside an FPGA, and these are Arctic 7 LUTs, which are quite capable. And so starting on the left here, we started off at about 1,200 LUTs. So that's when we released, and that's where we are today. So we've gone from 12,000 LUTs down to about 5,000 LUTs, which is pretty cool. And over time, we sort of had ups and downs. So this drop here from 12,000 down to about 10,000 is where we removed the second GPR port. The increase here is where we added the iCache, so initially that cost us quite a bit. And this bit here is actually where we added the divide instruction added by Paul, so that was added a little bit, but not that much. And then this large drop here is actually 3 big optimizations that we found. So one was put the register file in LUTRAM. The second was Paul wrote us a new decode, so that just saved us about 4,000 LUTs. And then there was a new iCache that Ben wrote. He rewrote that and made sure it was in block RAM. So that's that big jump down there. And sort of since then, it's kind of trended downwards. There's been a few ups, been a few downs, but we're keeping a much better eye on this LUT usage as we go. But I think it's really great that we've improved the core, made it better, and added more functionality. But halved the size of the thing, more than halved the size of the thing, which is fantastic. So board support. So we've been concentrating on the Xilinx parts for now. So FuseSock is this really great tool that we discovered. The first commit that we got, the first pull request we got was this Olaf guy who runs FuseSock. And FuseSock is this nice wrapper around the proprietary tools like Vivado. And it means that you can just run a couple of command lines and you can build your FPGA without having to open up a giant GUI and import files and all that sort of stuff. It's sort of more make-friendly, Git-friendly ways to build FPGA images. So we've got board files for these, or 5 boards here actually. So we've got the Nexus A7 card, Nexus video card, the ARDI A7 35 and 100. So this is quite a popular board with our developers at the moment. I think Anton's actually got one here if you want to have a look. Here it is, sorry. That's the ARDI board. For people, it's nice and small and powered off USB and quite capable. And the last one here, the CMOD A7 board, which is again another Arctic 7 board. And that's only about a $100 board, so that's pretty cheap. On the software side, we had MicroPython at launch, but we've now got MicroPython upstream, so you can download MicroPython from their main repo and run it on Microwatt. So it's all there, ready to go. You don't have to run my copy or Anton's copy or whatever. You just upstream MicroPython, it's there. We spent a couple of weeks on Zephyr. Zephyr's a nice little IoT operating system. It doesn't require an MMU, but we spent a couple of weeks porting Power and Microwatt over to Zephyr, and we've now got preemptive and cooperative multitasking. We've got a great little demo out in the booth. I think we're running Snake on that, so you can see that running. Zephyr's great. It's tiny, a great community. So it was nice being at the Open Source Summit recently in the last couple of days. There's a whole bunch of developers there. We've been talking about what our next steps are to get our port upstream. Other software developments, we've got someone in our lab ported PForth for some reason, but fun. People come out of the community and they want to do stuff, so that's what we love. That's what we love about this. And Anton did a talk at ORConf. ORConf is an open design, open sort of EDA tools design conference, and it was good. They invited us along. They invited Anton along. Say, come and present about Microwatt. Increase our diversity in open design. So it's really great. These guys are, it's a fantastic world now of open source design tools as well as having the designs themselves open source. So, moving on to some design details inside Microwatt. So the first question we often get is, why did we choose VHDL? VHDL we partly chose because we were familiar with it. Both Anton and I were sort of familiar with it. Also inside the Power org, inside IBM, we do use VHDL very heavily. So that was one of the reasons we chose VHDL. The other reason was, as Anton alluded to before, GHDL was the simulation tool we used to start with. And that's a fantastic open source project. Gave us a lot of confidence that it would work really well, that VHDL would work really well. It's got great VHDL 2008 support, and Tristan, who runs it, provides great support for it. So that were kind of the two main reasons why we chose VHDL. I guess a question for the audience, hands up. So who would identify themselves as a software person or a hardware person? So software people, hands up. Okay, a bit more than half. And then hardware person. Okay, so probably more on the software side, maybe 60-40, 70-30 for the record. So VHDL is different to writing C. For those who are familiar with hardware, it's about low-level concurrency. It's not like software where you've got instructions that run sequentially. Everything happens in VHDL. Everything happens in hardware all the time at the same time. So that you've got to sort of change your mindset when you're writing VHDL. But if you do want to get into VHDL and get into Microwatt, there's a tutorial that we found helpful. I'll give these links at the end, so you don't have to take a photo right now. I've got some links at the end. But that's a really great tutorial that we used to help you get into VHDL.
So one thing I got both internally and externally, the first thing as it went out, people would comment, they're like, this looks like a software person wrote it. Well, it's true, a software person wrote Microwatt. And there's a positive and a negative to that. I guess the negative is it wasn't particularly optimized. I wasn't thinking about how I was going to lay this out particularly well in the pipeline or how I was going to make my Fmax and all that kind of stuff. On the other hand, I was trying to use high-level primitives, right? So I didn't want to build at the gate level and design at the gate level. I wanted to use if statements, and I wanted to use case statements, and all these things we use in the software world that are available in a lot of these languages and often do work really well. So the hope was it was simple. A software person could kind of look at it and make sense of it, and then maybe be useful on top of it. One thing I found on the internet, and we have kind of used this, and as we have optimized, we might have gone a bit away from it, but trying to consider this in a way that was simple for me to get my head around and other people. And the problem with VHDL can be, as Mikey said, everything happens at once. So you may write a really big module with a lot of parallel things going on, and for someone coming fresh to it, it's really hard to get their head around. And I mean, we see this both in our internal hardware projects, and I'm sure other people do too. You hit a point of complexity, and then it's just very, very, very hard to someone who hasn't grown up in this piece of code to understand what the hell is going on. And so one thing we tried to do was kind of separate things out. The link will be at the end. But the idea is just to try and separate what was going on into a few very simple, two different processes, and each module was small enough you could look at it, you could understand it, you could understand inputs, outputs, what was going on. So A, a software person, or B, just someone who hadn't seen the core before could kind of get into it and understand it. And so we don't want to go into details specifically around clocked and combinatorial processes. If you were getting up to speed and you look at some of those tutorials, you'll start getting your head around it. But the important thing is we're really trying to keep things modular and simple. We'll talk a little bit about the microarchitecture. So from coming green from a software side, you do have to understand pipelining and kind of get your head around it. So maybe we'll start there and talk a little bit. For anyone who's gone through hardware at a university, you've probably all had to build a standard risk pipeline. And I think if you go to Wikipedia or anywhere online, it'll look something like this. And so basically when you think about it, what do you have to do? To start with, I have to fetch instructions. I've got my instructions, now I have to decode them. What do they do? Is it a load? Is it a store? What registers are impacted? Do I have to read and write any SPRs, all that kind of stuff? Next, we have to execute it. So you adder, you rotate, all those kind of things. The next stage, well, maybe that instruction is a load and store. So we have to go off and we have to read memory or we have to write memory. Finally, you've got all this state. You might have loaded memory, you might have done an add. You need to now commit it. You need to write it back to, say, your register file. So that's kind of where we started. And that's, as I said, a really, really simple pipeline. If you look at CPUs today, the problem is that as frequencies go up, the pipelines grow. So looking at this, firstly, was as you build a pipeline, what happens? Well, the pipeline is n stages, and you have potentially n things going on. Now, to get that going is quite complicated. Lots of bugs, lots of complexity. Our view was get it functional, get a CI around it, and then rapidly develop so that you had a functional core that we can then add complexity to. So one thing we did was basically one instruction through the pipeline. That was stage one. So what would happen is this one instruction would go through those entire stages of fetch, decode, execute, right through to write back, then the next instruction. And that was reasonably easy to make functional. And then we had something that worked, we had a CI around it, and then we can add hazards, we can add pipelining and all that kind of stuff afterwards. So I thought we'd just quickly go through and explain in a little more detail what's going on at each of these stages. This is what we have today. So it looks a lot like that standard pipeline. There's a little more going on, and we'll talk a bit about it. But it's still pretty simple. So if we start, again, we start with fetch. So at that stage, we basically need to work out where we're fetching from. And the first stage is very simple. Most of the time, you're fetching from the last instruction plus 4. What else might happen? Well, you might have an exception come in, or you might have a reason to redirect a branch. And so that little stage is doing not much. It's trying to work out where we're going next. The next stage, we have an iCache. And so we have a very simple iCache. And basically, its job is probably most people know what a cache is, but its job is basically to put a buffer between us and memory. It's a long way to memory, especially if you've got DRAM. You need caches in between the CPU and your RAM. So it is basically storing instructions for us. So if it's in there, great, we grab it. If it's not, we stall and we go off to memory and then fill it, and then away we go. And so that's iCache through to fetch. At the next stage, we're talking decode, and Power is a RISC architecture. We have 32-bit instructions. It's pretty easy to work out the boundaries every 32 bits. And on top of that, then we need to look at what the instruction is. And so again, it's relatively simple. We have opcodes. We have major and minor opcodes. You can pretty easily parse what the instruction is, what registers are read, all that kind of stuff. So in that first set of decode, what we basically do is that first stage. In reality, it's a big table. And so we index into the table, and it tells us what sort of op are we doing? What sort of registers are we updating? Is it a carry op? Is there a branch? All this kind of stuff. And then in the second decode stage, we then act on that. And so at that stage, we start to work out, okay, what are we going to need for execute? Okay, we're going to need these GPRs. Well, we're going to need to read them and all this kind of stuff. Decode 2 is maybe a bit like issue. Maybe we've misnamed a bit. But bottom line is we're getting ready to execute. We've got, by the end of decode, we've got all of the state we need to execute, and we know what we're going to do, what op we're going to do. And so we go through then to execute. And there's a lot of places you can go at this stage because there's a lot of different things you can do. And so off to the side, we have what we call slower instructions. So these are more complicated ones. Multiplies take multiple cycles. Divides, pretty horrible. They take a number of cycles to do. And loads and stores, again, at the best case, they'll go quick. At the worst case, we're going to wait on DRAM, and that could be hundreds of cycles. So they're kind of the slower instructions. Executes everything else. 64-bit adds, rotates, logical ops, all that kind of stuff that happens in a cycle. And so at that stage, we've kind of branched off, and then at the end, then we come back into write back. So at that stage, we've got a set of state that we need to write back, whether it be GPRs or anything, and that's the stage where we basically then write them back to the registers. So a little more complicated than the RISC pipeline, but not much. If you look at the code and you look at how we laid things out, this kind of gives a bit of a breakdown of how we build things up. So, we aim to be very modular. VHDL is all about modularity and building things on top of things. And so we start from the core out. And so we have a core, and then we have an SoC, which builds on top of that core, and that includes things like memory and the UART. And then on top of that, we have what we call top level, and that's everything. So that's everything that you need to, a top level is basically everything you need to run on your FPGA. So it includes things like your clock control and your reset control and that kind of stuff.
Thanks, Anton. We just wanted to run through a quick demo, and this is a demo of us running MicroPython on Microwatt, and this kind of shows how easy it is to get going. So it's kind of a quick demo, but you can see here we clone the MicroPython from upstream MicroPython. See, that's cloning. We go into the ports directory, we just type make, a couple of seconds, and it's built. Get yourself a nice image. Then we go and clone Microwatt from Anton's tree. Go in there, type make. You can see VHDL compiling it. Simple as that. Then we'll link MicroPython binary over into Microwatt, into our RAM. So we just link that file over. And then we just run Microwatt, which is the core test bench. And you can see MicroPython starting here. And then I'm just typing 1 + 2 and see if it works. And there you go. So you can see kind of in a few, like 30 seconds, a minute or so, cloned a couple of trees and you're up and running with Microwatt. It's really, really that simple. So in the future, what do we want? So in progress, these are things that we have, but they're not in the upstream tree yet. We want to continue leveraging more open source I/O components. There's a great project out there called LightX, which has a whole bunch of components. And one of the things that we have support for is the light DRAM. So if we want to attach DRAM into our FPGA, we've now got support for that, which we're trying to get upstream, thanks to Ben. But we want to keep leveraging more and more of these open source I/O components. We want to get more diversity in our FPGA. So at the moment, we're using a lot of Xilinx parts. The Lattice ECP5 parts are really quite capable. So we want to start doing that. We have actually got running on those, but we don't have support upstream for it yet. We're hoping to get Fuse SOC support, so we're working with the Fuse SOC maintainer, Olaf, to try and get Lattice Diamond support. And we're really hoping we'll get that. Lattice Diamond is the compiler for the ECP5 devices, like Vivado is for the Xilinx parts. So we're trying to get Fuse SOC support to make that easy. That's still kind of a work in progress. We're also working with Tristan, the GHDL guy. So he has a front end. So sorry, stepping back a second. The SymbiFlow is the open source toolchain. So that's Yosis and NextPNR. That's an open source toolchain to take your design and turn it into a bitstream you can literally flash on your FPGA. And they've got production quality support for the Lattice ECP5 devices. Unfortunately, SymbiFlow at the moment only takes Verilog input, but with Tristan's work, we're going to have, hopefully have GHDL synthesis front end to that, so we'll have VHDL into Yosis and NextPNR, and we'll be able to have a complete open source toolchain through from Microwatt to your bitstream you flash on your FPGA. Still, again, that's a work in progress. And once we get that, we'll have more board support. So there's more ECP5 support. So there's the ECP5 dev board, which is really quite a cheap board. And there's the Orange Crab from a developer in Australia, actually. So we're hoping to get more of those. More, looking further, things that we don't actually have yet, but we would really like. We're concentrating more on the core. So we'd like to get fully pipelined. Anton's described the pattern. We'd like to get fully pipelined so that we can run one instruction per clock cycle, per core clock cycle. Floating point, been a few discussions around that, but we'd like more, and we'd like to add floating point. And one of our big goals here is to get Linux running. So we can't run Linux yet. We don't have enough supervisor state. We don't sort of have that user space and supervisor state yet. We really just have the user space part. We also need a memory management unit, so we need to virtualize our memory. We don't have that yet. And we probably need some sort of IRQ controller, and we need to add exceptions and things like that into the core. We also want to get some more of our verification tools out. Mandy sort of alluded to this in her keynote this morning. We've seen huge advantage in having a make check and having good CI and Travis and all those sorts of things. So we want to get more of those tools out so we can keep our core stable and working. Other future directions, this is up to you guys. So come and talk to us. If you've got ideas of where you want to take this, or where you think we should take this, come and talk to us. We'd love to hear your ideas. So this is the slide you can take a photo of if you want some references. So we've got an OpenPOWER ISA BOF later today with myself and Anton and Mendy. There's also tomorrow there'll be a BOF specifically on Microwatt. So if you do want to talk about some future directions, if you've got an FPGA you want to try and get running, come talk to us at that BOF tomorrow. And there's a few links here, the two we gave during the talk, and there's a third one here, the Talis Space. He's the guy who actually produced our logo, the Microwatt logo, but he also added a beginner's guide to hacking on Microwatt. He went through and just added a random instruction And it sort of goes step by step how he did it. It was a snapshot in time of the code, and the code has been moving a bit, so it may be a little bit behind, but it gives you an idea that Cameron, I think, who wrote it, he's not a hardware guy, but he found it very easy to add stuff, so please go and check that out as well. This slide is sponsored by IBM Legal, and thanks very much. Did you guys have any questions from the audience? Oh, please.
I was just wondering, you said your core is targeted for specific boards or something. Do you actually use platform-specific macros for block RAM instantiation or something? Because in general, what you described seemed pretty general, that you can roll it out on any FPGA that's large enough.
Yeah, we're trying not to use, so we're using inference for a lot of stuff, for block RAMs and stuff. So as much as possible, we're trying to be portable. Yeah. A lot of it's just been access to it, tooling and all that kind of stuff. So, we're really interested to get on the ECP5 board. It shouldn't be hard to do. It's just more logistics. But yeah, there are some optimizations. So for example, some work that Paul McHarris did around some of the rotators. He's built it thinking about Xilinx LUTs, so without going into too much details for people that probably don't care, but the specific architecture, just to be optimal, but it is still going to be functional on, say, an ECP5. So yeah, as much as possible, it should be functional. Maybe it'll use a little, be a little less optimal. We have thought about perhaps we'll always have the base level, always have the base level performance model, but we might have some optimizations in a few places perhaps, but always having that fallback. So for example, if we do end up putting in an optimization for, say, a Xilinx FPGA, we'll always have the fallback, which is a more generic thing. But yeah, the aim is to be portable. We want to get it running on as many places as possible. And the reality is probably the only limiter is, at the moment, we are focused on 64-bit. So that means it's a minimum number of LUTs, really. We have thought maybe we'll play with 32-bit, but it's not a focus at the moment. As Mikey showed, at the moment in at least Xilinx, LUT speak, we're at about 5,500 LUTs. And so that does set a minimum bar for what an FPGA might support. As much as I'd love to, and we're going to try and get on, say, an ICE40, we probably are going to struggle with an ICE48K, just because the LUTs are less capable and all that kind of stuff. But the aim is to drive it down as far as we can, right? Get it on cheaper boards, get access to more people to get access to it. Yeah, definitely.
Any more questions?
Yeah.
Did you use any of IBM's VHDL from
Nope. It was a from scratch implementation.
So the question was, did we use any of IBM VHDL?
Yeah. So one of the things was we really had from start to finish 2 months to make this happen. And so, as much as it would be interesting to start seeing, some more of our designs become open, in that time frame, the decision was we'll build something from scratch. And so, as I said, I sit more on the software side, but I do have the advantage that I have, I guess, through osmosis, got a fair bit off our hardware teams over the years. So that has probably helped us get here this quickly. So that knowledge, I think, has been useful. But no, we haven't used anything specifically. It's completely, from scratch. Very good question. Mindy alluded to, the fact that we're looking for a bigger, longer-term engagement in the open hardware world, and I'd say probably stay tuned on that. I think, yeah.
So, no plans to the software to hardcore yet?
Sorry, I didn't quite get that.
So, there are no plans to the software to hardcore yet?
Are there plans to turn the software into a hardcore yet?
At this stage, we're focused on FPGAs. As time goes along and it gets more capable, there's nothing to stop that from happening. Personally, I think that'd be fantastic. The good thing is that the licensing, is already in place, right? Because of, as Mendy was saying, now it's able to be implemented royalty-free and with a patent grant. There's nothing stopping that next step. And, you know, my hardware friends would say there's a number of steps between getting something on an FPGA and actually building it in silicon. But sure, you know, we'd love to see, you know, an implementation on silicon, absolutely.
Out of curiosity, why didn't you base it on the PPC 405? I think it's called.
Did we? No, I mean, our course, oh, why didn't we? Going back to the discussion with Ned just earlier, it was more a timing thing. So basically, there were a couple of aims here. Get something out really, really quickly. So we had literally a couple of months to get something out. And two, make it simple enough that a software developer could understand it. And so even simple cores, by the time they are built and they've gone through the rigors of kind of timing, they're quite complicated. And so, yeah, you know, while we do have a lot of 32 and 64-bit PowerPC cores inside IBM, yeah, the tactical decision was let's build something up from scratch, and that was Microwatt. You know, and in parallel with that, you know, we're quite interested to look at, you know, some other steps we might take. And, you know, as you say, we do have a lot of cores inside IBM, including the 4XX.
One thing we have reused is the wishbone interface. I'm not sure we mentioned that during the talk. So we do the memory interface, the UART interface is a wishbone interface, which is an open standard. So it's not an IBM standard or anything like that, but it's a way for us to enable us to hook into this open source world so we can plug more modules in. So we're not completely from scratch. We do have that sort of standard interface.
Yep. And the other thing there is, because we use the wishbone interface, things like DRAM came relatively simply. And so if we'd taken an internal core, there would be work to either port to an open bus or port, you know, an FPGA DRAM controller or something like that. Since we used wishbone, it basically meant that all of a sudden peripherals can start plugging on. And, you know, it's never that easy, but it was much easier than I thought. Ben Herenschmidt in our team back in Australia did that work, and, you know, we gained a lot from it in a short amount of time. Any more questions? I think we're done. Well, thank you very much for turning up, and we'd love to see you play. You know, download it, play with it.